Hello, wonderful people of the internet. Welcome back to another lecture for the MIT course 18S191 on computational thinking. Today, we're going to be continuing from last week when we did two-dimensional ray tracing and moving into the fully 3D realm. Hopefully, it'll be pretty interesting. As a quick note, the video will be slightly different than last week's video just because I don't have as much editing time, so I'm trying to minimize that. But I do have a whole bunch of cooler visualizations, so hopefully it'll all work out. Before getting started, let's do just a little bit of bookkeeping. One, the homework set from last week will actually be done this week. So, to be clear, this week we will be doing a 2D ray tracing example in homework. Next week, we'll be doing a 3D ray tracing example in homework. So basically, the ray tracing homework will come 1 week after the ray tracing lectures. In addition, this particular homework set will be available on this upcoming Thursday, and it will be due next upcoming Thursday. Now, as I mentioned, this lecture strongly depends on the lectures from last week. That is to say, if you did not watch those videos, please go back to watch those videos before watching this one. Last week, we created this image over here, which was a very simple two-dimensional ray tracing example for spherical aberration. The idea is that individual rays of light come in over here. They then enter the lens and refract towards normal. And then as they leave, they refract one more time, creating a semi-focusing event at this area right here. During the lecture last week, we talked about how to do this if we were time-stepping light. That is to say, if we thought of light as individual photons that were moving forward with time. So every single time step, we simply moved light forward by some little bit depending on what direction it was moving in. On Thursday, we talked about a billiard model, which was useful for thinking of event-driven simulations. If we were to redo this visualization in an event-driven manner, the idea would be that instead of time-stepping light and moving it forward one small time step at a time, we basically figure out when it's interacting with the sphere. So for example, here and here, and then we apply the refraction event at that step. After refracting, we have a new velocity, and because we know the next point that it intersects with the lens, we can basically just move light forward by a giant time step here to here. Now, for the purposes of this lecture, we'll assume that this exercise has already been done, so keep that in mind as we move forward. The two prerequisites for this particular lecture are 1, understanding how reflection and refraction work, and 2, understanding exactly how event-driven simulations work. Now, at the start of lecture yesterday, I brought up this image over here, which is a really cool ray tracing image in 3D. I'm going to be honest, we will slowly build ourselves up to something that kind of sort of resembles this over here, but there will be a few key exceptions. For one, we're not going to be doing arbitrary shapes, we're only doing spheres. And 2, because I'm not really much of a 3D modeler, it's not going to look as pretty. It'll still be cool, and it will still teach you all the details that you need to know. It just won't be quite as pretty as this one. Finally, to finish up the bookkeeping for this week, next week we'll be having a guest lecturer and we'll be setting them up with the extra lectures this afternoon. So if the mini lectures this afternoon seem a little bit unrelated, that's because they are, and they're setting up guest lectures for next week. Okay, so without further ado, let's talk about what we're actually going to do today, which is generate this image in here. So what exactly are we looking at? We're looking at a 3D ray tracing example of a whole bunch of different spheres that are all doing kind of different things. So for example, this lens in here is purely refracting, whereas this lens up here is purely reflecting. This one over here is just blue. Don't know why, it just is. And all the other spheres in this visualization are somewhere between reflecting, refracting, and some pure color. For example, this one here is red and also refracting. This one is green and also reflecting. By the end of today's lecture, we should be able to fully understand this image. And to be clear, we're going to be talking in predominantly broad strokes. The fine details will come in Thursday when we'll be doing a live coding session to show you all of the gory details. So let's actually start at the start here by going back and describing what ray tracing is, by going back to the example we had last week, when I stared lovingly at a mandarin with some sort of light source in the background. Here, again, the idea of ray tracing is that light comes from basically a variety of sources. Here we could say this lamp, and it hits this mandarin over here. Then the mandarin reflects orange light all the way up into my eye over here. And in this way, I can then see the orange nature of the mandarin in my eyes. Now, last week, again, we focused on showing the rays themselves being visualized in 2D, but today we actually want to do a full 3D visualization. So how exactly are we going to do that? Well, what we're going to do is we're going to draw a little screen right here. And we're going to say that the light that comes from the Mandarin pierces through this screen. Now, this screen is basically a two-dimensional set of pixels. So the idea is whatever color information is being transferred from the Mandarin through that screen will then be projected onto that pixel that it hits. Now, this is obviously different than what we did last week, but this is how traditional ray tracing approaches work. Now, from here on in this lecture, instead of looking at my eye, I'm going to assume that my eye is actually some sort of weird camera that is accepting all of the light from the outside. So now we need to talk about that in more detail by talking about both the camera and something I'm going to call a skybox. So what exactly is a camera? So let's redraw that scene we had just a second ago. We have some sort of light source, some sort of orange, and then some sort of camera over here accepting light from the orange. Again, light will come from here, and then it will bounce back with color information towards the camera over here. Now, here's the thing. The light source is actually emitting millions upon billions of rays in all directions, right? So if we're going to simulate all of these rays of light, we're quickly coming upon a computationally infeasible problem. Remember, the only thing that we actually care about is the light that goes through our two-dimensional screen in here. So what we're actually going to do is instead of measuring from some arbitrary light source to the eye, we're actually going to go in the other direction. And we're going to go from the camera to the objects and have them bounce back into some sort of light source. Anytime they hit an object, the ray is then just going to get that color information from the object. So the ray goes from the camera to the orange, it then turns orange, and then it goes back to the light source. But okay, here's another issue. The light source is also a point source, right? And in actuality, when you think about the world around you, well, it's a whole world. It's not just a number of light sources, it's like this weird image that you're actually looking at, right? So instead of thinking about light coming from specifically a light source, we're actually going to think of light coming from a huge number of objects around us. And that is the concept of a skybox. So I'm actually going to do something a little weird here and pull up one of my favorite video games called Guild Wars, and I'm just going to stare up at the sky. If you look at the sky here, you're going to see a bunch of stars. And we know that these represent burning balls of gas millions of light years away. But to game designers and to us in actuality, there's really no big difference between burning balls of gas and fireflies painted on some weird bluish black thing. So because game designers don't want to implement burning balls of gas billions of light years away, they instead just paint fireflies on some sort of surface. So what does that surface look like? Well, let me just go ahead and try to draw it for you. So here I'm going to erase the light source. And then I'm just going to draw a giant globe that encompasses all of these objects, right? The idea here is that now light comes from the camera, hits the orange, collects the color information from the orange, and then it reflects back off into some sort of three-dimensional globe that collects all of the light. And now this three-dimensional globe is what we're going to call a skybox. It is essentially the sky. Now we can technically color the sky in any way, shape, or form we want, but we're going to choose a very particular type that allows for us to basically collect better debugging information later. Okay, so what does this look like in code? Well, for the purposes of this particular video, we're going to have some sort of abstract typed object over here. And we're going to have our skybox within that type of object. It's going to have a position and it's going to have a radius. Now, this is very similar to a sphere. In fact, it is a sphere. We're just somewhere inside of the skybox. And because we know from last week how to tell when we're interacting with the inside of a sphere, we should always be able to tell at what location we're interacting with our skybox on. Now, the camera is slightly different. Here, what I'm going to have is a set of pixels, right? Now, this pixel information is exactly that two-dimensional screen where light pierces and collects color information. But I'm also going to have a physical size for the aperture, and that's different than the pixel information. The physical size of the aperture is the size in real-world units of how big that doorway is to look through. Finally, the last two things I keep are focal length and a position. Now, the position is the position in real-world units of where that camera is located. The focal length is a bit different, and I'm just going to scroll up here to try to describe exactly what that is. So here I'm going to draw the camera screen in here. And then I'm going to draw a circle back here, which represents where the camera is viewing from. Now, light needs to come from this source outward, which basically means if we're projecting light from this source, we're going to have rays that span from all the way up here to all the way down here. Now, if we move this source backwards a little bit, maybe all the way back here, all of a sudden the rays don't span as far. And here the distance from where the light is being sent from to the screen is going to be called the focal length. Essentially, you can create a fisheye lens effect by lowering the focal length, and you can see the scene more directly as it looks by increasing the focal length. If you make the focal length infinitely large, you're essentially sending a set of parallel rays into the visualization, which is exactly what we did last week. Now, before moving on, I need to say one thing in particular, and that is that our camera struct over here has no real direction information. And that was on purpose. Here, we're going to force the camera to point exclusively down in the Z direction. We could choose to have it point in a number of different directions, but here, for the purposes of this lecture, and probably also for the homework set associated with this lecture, we're going to have the camera pointing down in the Z direction. The reason we're doing that is because, quite frankly, moving this camera around in three-dimensional space is kind of a pain. You have to think about not only its position and its focal length, but you also have to think about the rotation of the camera itself. And I feel like it distracted from the purpose of this lecture because every time I tried to do anything with the camera, I ended up focusing almost entirely on camera math, which wasn't exactly where I wanted to go. So now let's talk just a little bit about the different types of objects that we could potentially see in our visualization. Obviously, we have reflecting objects and refracting objects, which are both objects that we talked about last week. But in addition, I'm going to add a third type of object. This object is just some arbitrary color, and it will just return color information. So let's say we have a ray of light, and it's going to hit this object here. Well, in principle, it could do one of three things. One, it could reflect off in this direction here. Two, it could refract in this direction here. Or three, it could just stop for a second and give us the color information, in this case, blue. For this purpose, I've created this weird kind of texture surface struct called just surface. The idea is that it has some reflectivity, R, some transmission coefficient, T, and then some color, C. Now, in actuality, these objects could have some amount of reflectivity, some amount of transmission, and some amount of color added to every ray of light that hits it. That is to say, every time we hit this ray of light, actually, we're going to spawn potentially 3 more rays of light. One that's reflected, one that's transmitted, and one that just stops at that object and returns color information. We're going to get back to this in just a second, but before continuing, there are 2 things I do want to talk about. One is that our struct for our surface actually has a number of constructors, just to make it a little bit easier for us to create this surface. And 2, there are a whole bunch of different objects that we're not going to be considering. The first is diffuse objects. That is to say, objects that scatter light in some direction. We're not dealing with this just because it's a bit complicated, and again, I think distracts from the overall purpose of this particular lecture. We're also not going to be describing weird shapes, and I'm just going to draw a weird shape over here on the side, right? Now, the reason we're not considering weird shapes isn't because our ray tracing methods can't deal with weird shapes. It's that if we're going to create these shapes, we have to basically define the normal for this entire object. So the normal here, the normal here, the normal here. Because the normal is so important for both the reflected and transmitted light, we have to basically know how that light is going to interact with this object. Parameterizing arbitrary objects is kind of a pain in the butt, and it's not something I wanted to deal with here because, again, I felt like it distracted from the overall purpose. Now, one thing that doesn't exactly distract from the overall purpose of this lecture that we are also going to skip is shadows and light sources. Now, the reason we're not going to deal with this is simply because we don't have time, not because they're not important. I do encourage you to look up other sources that talk about how to deal with shadows in particular. Heck, maybe we can touch on them a bit on Thursday, but probably not going to happen. Now, let's talk about the Skybox a bit. Here, we're going to say that the pixels are going to be colored based on the location when they hit the Skybox. That is to say, if its X position is between negative 1,000 and positive 1,000, we're going to create a smooth gradient of red. If its Y position is between negative 1,000 and positive 1,000, it's going to be a smooth gradient of blue. And if its Z position is between negative 1,000 and positive 1,000, it's going to be a smooth gradient of green. Now remember, our camera is facing exclusively down, so if we just take a picture without anything in the scene, we should expect to see no green, because green should be exclusively behind us. And that's exactly what we see in our image over here. No green. So what if we wanted to see the green background? Well, we could do a number of things. We could put a flat mirror in front of us that points backwards. We could even just make the camera face the other direction. But because we're talking about ray tracing and I had that visualization of a bunch of spheres, I think what we're going to do is we're going to show a single reflecting sphere. That's shown in this image over here. Now again, bringing back information from last time, how exactly does this visualization work? Well, the idea is we have some sort of light coming in and reflecting off the surface of the sphere. Now, I'm not going to show any math here because we showed all the math last week, and there will be more math in code on Thursday. But just remember that this depends strongly on the normal from the surface of the sphere. That is to say that the angle of reflection is the same as the angle of incidence coming in. So as we're looking slightly down onto the sphere, you'll note that the green is kind of slightly off center. And that's because the rays of light are coming from the camera, hitting, and then bouncing downward towards the green in the background. Now, because this is only a single reflecting sphere, and the sky around it is this really weird gradient, it kind of looks a bit funny. In fact, if you only show a single sphere in any of these images we're about to show, they all kind of look a little bit funny. But when we start showing more and more spheres, it gets more and more interesting. But that brings up computational demands that we'll talk about later. The important thing to note here is that this reflecting sphere is basically only seeing the skybox. Light will come in, hit the sphere, and then will leave and hit the skybox. At this point, all rays of light stop at the skybox. And that's how we're doing this simulation. It reminds me of the famous quote, "No matter where I look, I only see sky." So now let's talk about the next thing, which will be color. So here we have kind of a similar simulation as we saw before. We have some sort of skybox over here in pink, and then we have some sort of colored object here in the center. Except here we have kind of a different situation. The ball is entirely blue. So now what exactly is happening here? Well, light is coming from some source and it's hitting the sphere, similar to what it did before. Except at this point, what we're doing is we're actually stopping the simulation for that ray. We're saying, once you hit this object, just return the color blue and don't go any further. So when we're interacting with colored objects, this is the only time in our simulations that the rays of light won't stop at the skybox. Every other time, whether it's reflected or refracted, it will go all the way to the edge of the simulation. This reminds me of another famous quote. When you're moving around at the speed of light, it's hard to know how to stop. Finally, we need to talk a little bit about refraction. Now, we've shown the 2D visualization of this a number of times already in this lecture, but I'm going to draw it again here because I think it's important. Light basically comes from any location, it enters a sphere, it refracts towards the normal like this, and then it refracts again out here. And if we send another ray of light, it comes in here, refracts again towards the normal, and then refracts again out here. Now, when we look at this little bubble over here, you'll note that there's some weird green over here on the edge, and yellow, and blue over here. And this is exactly what we'd expect to see. First of all, we see this kind of weird mirroring effect, where blue is on this side, and pink is on this side. That's exactly what we expect to see, because the rays of light over here are swapping. That is to say that light that misses the sphere entirely will hit this location of the sphere and return pink. But a ray of light that actually goes through the sphere will hit this over here and return blue. As another note, this angle of refraction outside of the sphere is actually deeper, which means we expect to see some color that is even more blue than you would expect to see at that particular location. That's why we start to see some green and yellow, because we're starting to pull locations on the gradient that aren't in the original image here. Okay, so at this point we have some pretty pictures, right? We have a reflected sphere, we have a refracted sphere, we've got a sphere that's entirely one color, but it reminds me of at least one more famous quote. But where's the computer science? So I want to talk just a little bit, not necessarily about computer science, but software development, and in particular about how you iterate on an old idea to come up with something new. See, here's the thing, that refracting sphere actually took me a significant amount of time to make, like somewhere between 10 and 20 hours, even though I already had an image of it the week before. And that's because in going from this image that we had to a 3D example, we had to change little bits of the code here and there, and by changing a bunch of little bits of the code actually changed in a rather large way. So large, in fact, that my refraction function didn't actually work the same way it did before. So I consistently used this test case as a way to make sure that my code was working the way it was supposed to work. In addition, I created a suite of tests, which basically takes the sphere over here and sends specific rays of light at the sphere to make sure they hit the wall at the appropriate location. I was trying specifically to get edge cases. So for example, I sent a ray of light that just barely kissed the top of the sphere. I sent another one that went through directly, just to make sure it worked as anticipated. And then I had a few other rays of light that refracted through, and I analytically calculated where it was supposed to hit the wall to make sure it actually did so in code. I'm not going to say I used full test-driven development, but those tests certainly helped me to make sure that my code is working appropriately. Which is why I encourage you guys, whenever you're writing code, really think about different test cases. Think about ways you can write code and think about ways you can test that code. Because the most important thing is that your code is working. Remember, your code is only as good as its tests. If you don't test a function, you can't reliably know whether that function actually works in practice. Okay, so now we're going to put it all together. Like I said before, when you have just a single sphere in some sort of weird gradient background, it looks kind of trippy. It doesn't really give you all the information you need. So here are three spheres side by side. One that's refracting, another that's reflecting, and another one that's just blue-ish. Actually, I don't really know what color that is. It's kind of like blue, white. I don't know why I chose that color. But anyway, the point is that we have all three of the different balls all together in one simulation. Now here's where things get a little trippy. Here I have three different blocks of code that all add together in the end. One block of code for transmission, another block of code for reflection, and finally a third block of code for coloring. In the end, we say that our ray color is actually going to be a combination of these three, and we use the transmission, reflectivity, and alpha values to determine how much of that ray's color depends on the transmission, reflection, and the coloring that are spawned every single time we interact with an object. So here, if you note, I'm creating a refracted ray in the transmission bit here that then propagates a refracted ray forward with time. I'm doing the same for the reflected ray, but not necessarily for the colored ray, because again, the colored ray is just going to stop at some location. I'm also doing a little check in each of these blocks just to make sure that there is some amount of transmission happening before actually doing the transmission. That is to say, if the surface has no transmission, it's purely reflecting or purely coloring, there's absolutely no reason to track a ray going further into the visualization. The truth is, as we add more and more objects to the simulation that are some weird mismatch between transmission, reflectivity, and coloring, we're actually going to spawn a whole bunch of rays that all do various things. If there are enough rays, it becomes actually computationally costly, which is why we do need to make use of parallelism, which was another topic that we covered last Tuesday. Okay, so now let's go back to the visualization we had at the very start of lecture, this one in here. The idea is I've got basically 6 balls that are just sitting in the middle of the visualization. Again, this one is refracting, this one's reflecting, and this one over here is just blue. Now, in addition, I created a bunch of just random spheres that are just in the background. This one over here is just a random sphere in the background. This one over here is another just random sphere in the background. And there's also one back here that's also just randomly sitting there. These were literally created at random just so that the reflected and the refracted balls can actually see other objects inside of them outside of the 6 big ones in the visualization. So now if you look at this ball, that's reflecting all the balls back in it. You can actually see that the ray of light that's coming from the camera will hit not only the reflected ball, but also this ball over here, and then this ball over here, and then it looks like even another ball after that. And every single time we have to deal with the event of that ray reflecting off of that ball. So we have some ray of light hitting that ball, it then hits another object where it then splits into some amount that's being refracted and some amount that's being reflected, and then both those rays go hit another ball that then could potentially split into refracted and reflected rays again. The point is, as we introduce more and more objects, this is why the complexity does not scale particularly well. In fact, because of this recursion, in principle, there are some elements of this visualization that don't do very well with parallelization. But all said and done, I'm relatively happy with this visualization, and I think it does encompass basically everything that we need to know about ray tracing. The idea is that we have rays of light entering the scene that can reflect, they can refract, and they can potentially just return some sort of color. Okay, so finally, we need to talk about where to go from here. And there are a number of different things that we could do. One is that we do need to talk a little bit about parallelization. Now, we talked about CPU parallelism and a little bit about GPU parallelism before, but in particular, when people do ray tracing, they typically do ray tracing via the graphics processing unit with some sort of weird GPU shader. If you're familiar with gaming, you probably recognize the fact that NVIDIA is really touting the fact that they can do some high quality ray tracing in their latest graphics cards. Again, this is because ray tracing is a very computationally costly endeavor. So being able to do real-time ray tracing is actually really cool, no matter who's doing it. In addition, if you want to do ray tracing for yourself, I do very strongly encourage you to think about lights and shadows and also arbitrary shapes. It's an interesting question about how to deal with meshing and textures and things like that. But again, the purposes of this particular lecture was to give a general overview for how ray tracing works and why it's important. Specific details were covered last week when we covered event-driven simulations, and we went through all the math for both reflection and refraction, and even more details will be covered on Thursday when we do a live coding session where hopefully I'll be able to show you all the ins and outs of this code in a way that satiates any itch you might have to just really delve deeply into the details here. Again, be on the lookout for the homework set this week, which will be for the 2D ray tracing example from last week, and the homework set for next week, which will be basically recreating this image in homework. That's all I have for now. Thank you so much for watching. Enjoy the auxiliary lectures today, and I will see you on Thursday.